One vector component that comes up often when looking at geometrical constructs is the cross product. So that's what we're going to look at in this video. If I have a B vector like this and the C vector like this, and this is the angle in between them, theta BC, then what you've often seen before is B cross C is equal to the magnitude of B times the magnitude of C times the sine of the angle between them. The geometrical interpretation of the cross product is that it tells you how not aligned two vectors are. That is, how perpendicular are they? Clearly, when they're more perpendicular, the sine of the angle becomes bigger, and you get a larger cross product. The geometrical interpretation, well, another geometrical interpretation is that if you have, say, a trapezoid, and you define this to be the C vector down here, and this one to be the B vector right here, that the area of this trapezoid is easily calculated as the cross product. So the area is going to be the magnitude of the cross product of the two vectors. The reason for that is that you can see that if I split off this triangle right here and add it over here, that it's the same thing, and I end up with a rectangle. The height of the rectangle is going to be equal to B sine theta, where theta is this angle right here, the angle between B and C. So this tells you the area. You'll see this in, say, condensed matter physics when you're trying to figure out the area of a two-dimensional lattice, for example. Also, in that context, sometimes you'll see things like a vector A defining one part of the lattice, a vector B, and this is supposed to be a three-dimensional picture, and C, and then you have this parallelepiped, something like this, and the volume of that is going to be the area of the base times the perpendicular, or sorry, the amount of A that's perpendicular to that base. So actually the way it ends up being is A dotted with B cross C, or any arrangement of those. So these two tricks show up a lot in upper level physics or in any kind of application where you're looking at volumes. Now, of course, the cross product, as you know, is a little tricky in some ways to write out what the component form should be. And you've got various tricks up your sleeves for how to write that. Let me briefly go over those. B cross C, as you know, is going to be this ugly thing right here, by cz minus bz cy in the x direction. Notice you get y and z with x. There's no, if you've got x hat here, you've got no x in the components. And then the same thing for the y component. It's going to be bz cx minus bx cz. Again, no repeated, if you've got y here, you don't have y here. And again, here, if you don't have z, or if you're looking at the z component, you don't have it in here. Cy minus by cx in the z hat direction. This can be written in a few ways. One of the ways that I like is something called the cyclic representation. The ith component, where I is equal to 1, 2, or 3, meaning x, y, or z, is equal to the bj ck minus bk cj, where I, j, and k are cyclic. Cyclic meaning so an ordered sequence of the integers involved. So 1, 2, 3 is clearly ordered, going from lowest to highest. I can push the 2 back, right? I can push this 2 back and this 3 back here, and I maintain the order. It's just shifted a little bit. Now it's 2, 3, 1. That's also cyclic. Notice I go 2, 3, and then go back to 1. It's just sort of cyclically permuting the indices. I can also push those back 1, both all in the same direction, and I'll end up with 3, 1, 2. That's also a cyclic order. And you can see how this works, right? The x component, the first component, is b2 c3, that's by cz, minus b3 c2, which is bz cy. And for example, the y component, the second parameter here, is going to be b3 c1 minus b1 c3. That's one way that I tend to memorize how this works. And this idea of cyclic indices comes up time and time again throughout lots of different areas of physics. The one that you're probably more familiar with from high school, and that is actually a good go-to, is that B cross C is the determinant of this matrix x, y, z, bx, by, bz. So this vector is the first row in this matrix, and then cx, cy, cz. And if you remember, the way that the determinant works is you get this minus this, okay, and you have this minus this, and then you have this minus this. And you can see how that works. X hat by cz minus x hat bz cy. That's this term right here.